So I'm going to give 4 lectures. This is separated from the other 3. The other 3 are in a different topic. So this is about the convergence of the planning problem for mean-field games and a rigorous proof for the Friedlin-Wenzel type large deviation principle for KPZ. Okay, so the talk is about, we're going to investigate the connection between a very singular optimal transport variational problem with a congestion term that connects 2 Dirac masses with a formulation for large deviations appearing in the physics literature. And the crux of the matter is a convergence result for the Euler-Lagrange system that behind the variational problem. Let me say about how we came across this problem. There was a young probabilist in Chicago at the statistics department who came and asked me whether we have any idea about how to solve the problem he was interested in. And eventually that became a long collaboration with Pierre-Louis. And so let me start a little bit about the large deviations. This is not a probability talk. And if you ask some probabilists, even some famous French ones, they think that everything had been done before, but we cannot find that. So this is a group of physicists. I'm not going to read their names, but there's a large literature, if you go around these names, of people where they do an ad hoc formulation for the large deviation for KPZ. Now, KPZ is a very fashionable problem, so let me just explain how we come to what we want to do. So after scaling, one can write the KPZ this way, where the square root of theta is the scaling factor is used, and the xi is a space-time Brownian motion. And we start with the particular initial data, which is the regularization of the logarithm of the Gaussian. Since xi, the white noise is in L2 in R cross 0, 1, the classical large deviation theorem says that up to a logarithm, the logarithm of the probability that the square root of theta xi is similar to some L function in L2 is controlled by that functional. So that's the classical large deviation you expect. So what the physicists say is that, okay, if we concentrate on the subset of the probability space where square root of theta is like rho, then the KPZ is approximated by this deterministic problem there, which there's not any more white noise. So once they do that, they start working with this problem, and they try to understand what happens at the limit. So here's what you want to do. So this is the problem we want to study. And formally, one can see, motivated by ideas from large deviations, that they're interested in understanding what happens as eta goes to 0 and the value of h at 1 goes to infinity. So after scaling and changing variables to epsilon, 1 over epsilon to the h, that large deviation principle is controlled by that functional. So this is the same quantity that was here. And that's the functional. So you solve this PDE, the Hamilton-Jacobi equation, with the given initial data, but with that constraint at 1 to be the value at 0, 1 to be 1 over epsilon. And they claim that the limit of that should give you the large deviation you want. Okay, so now let me connect it with the system I said. So it's a well-known fact that the Euler-Lagrange, this problem is convex, so you can find that there are unique minimizers, and they solve this Euler-Lagrange equation. So it's the Hamilton-Jacobi-Bellman equation with right-hand side rho epsilon, then a backwards, I wrote it in this way, a backwards transport for the density, and the initial condition for the u epsilon is x of square over 2 eta. At 1, 0, 1, the u epsilons are 1 over epsilon, and the rho epsilon is some multiple of Dirac mass at 1. the system appears ill-posed because you have an initial condition and some value at the end, but that's the role of the choice of the rho at the end to be a Dirac mass. And the constant here, the C, is adjusted so that we can have the u epsilon eta at 0, 1 to be 1 over epsilon. Okay, so I skip all these technicalities, but the constant C comes from that. In order to have this 1 over epsilon, you have to have a constant times Dirac mass at 1. Now, in the physics literature, when they put the limit at eta goes to 0, they talk about a narrow edge initial condition, while letting epsilon go to 0 corresponds to what they call the special zoom out of the KPZ. There are several levels of the large deviation thing. Most of them have been resolved in the physics literature, except that. That's the one that was open, and that's what these guys asked us to look at. Okay, so now I can start motivating what we do. Again, I say it's classical. It's that classical duality and variational type arguments tell you that this variational problem here is equivalent to that, where now the constraint is the backwards transport equation here with energy that is finite, starts, and I'm rescaling now, I'm looking at the problem without the C, without the constant times the Dirac mass, so I'm just putting a Dirac mass. So think of everything carrying over if I had the constant there, just to simplify the notation. And so the problem, the original problem, is equivalent to minimizing that. Right? So once again, we go with soup over the right-hand side, or L2 norm of the right-hand side, to infimum over that. And for this is something that people who work in mean-field games or anything, they know to say that as epsilon and eta go to 0, you would expect to get this variational problem at the limit. So you're going to have a Dirac mass at, which was there at, the limit will be because of the x squared over 2 eta there, and eta going to 0, that will give you Dirac mass at the origin. And the other one is there already, and you keep the energy. So the claim that the probabilist wanted to make was that the I epsilon eta converges to that, and that's it. That's the large deviation I wanted to prove. Okay. As far as we know, there is no complete proof for that. Even when they claim they have it, it's not there. And part of the reason is that in a lot of these large deviation problems, there is this magic trick in the proof they claim, which is to use what is known as Varadhan's lemma. So Varadhan's lemma is something that tells you that if you start with nice, let's say, set, you can do something and the variational convergence, the variation problem is almost immediate. And it's a powerful result that applies to everything. Here we are looking at something different. We are looking, if you like, instead of large deviations, we are more interested in the behavior of the fundamental solution of the problem. And that's a different ballgame. In the history of large deviations, that was done by Eisenkot, when he looks at the asymptotics of the fundamental solution of the heat equation. It's a different thing because you need to understand very well what happens at the singularity. While if you assume that you have something nice at the initial data, you don't have to worry about this problem. So the reason this is difficult is exactly that. Now, because you have to introduce this x squared over 2 eta, and I will explain why this has to be there, you break the symmetry. This problem, at least when rho is smooth, when the minimizer is smooth, is symmetric in time. So if you change time, t to 1 minus t, you get the same problem. While this one is not symmetric anymore because you have it's not symmetric because you have an initial condition there. So that creates a problem. And that's the difficulty with, this lack of reversibility in the dynamics requires the relaxation and so on. So it's like when you try to study the asymptotic behavior of the fundamental solution of the the heat equation, you have to put a logarithm of the fundamental solution, you have to put a logarithm of the Dirac mass. This doesn't make sense, so you approximate by a nice exponential. All right, so we're going to follow a different approach. We cannot prove the convergence directly, the convergence of the functionals, which a priori it looks silly because these functionals are strictly convex. You have everything you want about them, but you can really not really control the behavior near 0 and 1. And we're going to get that by looking at the corresponding Euler-Lagrange equations. So this is the Euler-Lagrange equation that corresponds to that problem up there. And the other one is the Euler-Lagrange equations that correspond to the problem with epsilon and eta 0. So, okay? And what we're going to prove is that as epsilon and eta go to 0, these solutions converge to these solutions in the right way. And in the process of doing that, we're going to get as a free the convergence of the functionals. So we're going through the Euler-Lagrange equations to get that. Okay. So the Euler-Lagrange equations, now everything connects with the title. It usually appears in a one-dimensional planning problem where you want to connect two Dirac masses from 0 to 1, let's say. As I mentioned already, the presence of the diffusion breaks down the symmetry of the problem. Because we want to have here, in principle, we want to have the rho epsilon eta at the origin at time equals 0 to be a Dirac mass. This you cannot do it, because if you could solve this problem, then you have a Brownian bridge with an L2 drift, and that's not possible to have. So it is necessary to relax the initial condition there to x squared over 2 eta. All right. So hopefully I motivated why we want to study the behavior of that as epsilon and eta go to 0. And let me state the results slowly. And then from there on, this is a very technical result that I will try to show you some of the ideas of the proof, but there is no way I can do everything, and because it's technical and it has to do with analyzing the behavior of the solutions near 0 and 1. Okay, so as I said, the functionals are strictly convex, but we are not aware of any proof directly with the functionals. And establishing the convergence is challenging because it's necessary to understand the singular behavior at 0 and 1. And for those of you who have worked on the planning problem in such kind of conditions, you know that it's difficult. Okay, so I'm going to state 3 results and try to indicate a little bit some of the proofs. So the first one is that what we call the planning problem, namely solving this forward Hamilton-Jacobi equation with this backwards transport equation is well defined with initial conditions Dirac masses at 0 at time equals 0 and time 1. So the first claim that this is well posed, and so indeed this has a unique solution under the following constraints. The solutions grow faster than x squared over 2t as for every t, as t goes to 0, you can estimate this product by rho squared x over x over 2t. The solutions are Hölder continuous, and they have finite energy. So under these 4 conditions, one can prove that the planning problem has a unique solution. I'll come back to that in a minute. The second is about the convergence. So the convergence result requires some constraint on the epsilon and the eta. So the assumption we have to make, we can do, is that epsilon times minus logarithm of eta to some power, which is strictly bigger than 1, but can be any power, that under these conditions we can prove that the solutions of the Euler-Lagrange equation at the epsilon eta converge to U bar locally uniformly at R open 0, because there it's Dirac mass. We can prove that rho epsilons eta converges in L2 to rho bar, which is what is needed to prove the large deviation. But not only that, but we also have that the gradients converge in L2, and the usual quantity there, which is that comes in the energy, the square root of rho epsilon times the gradient of derivative of u epsilon eta converges in L2 to that. Once we have these two statements, then it will follow that the two functionals converge. So all the work is to get that. Okay, now let's go talk a little bit about that. As I said, the difficulty is the singularities you have at t equals 0 and 1, which you need in order to prove these results. It's immediate with some elementary estimates to prove that you have this convergence locally in R, locally in L2, but that's not enough because we want to go down to time t equals 0. The global convergence, we can get it because we can estimate in L2 the difference between rho epsilon eta and rho bar using identities that come from mean-field games. That's the only connection for mean-field games. And as I said, we cannot solve this problem with u epsilon eta being it's 0 or plus infinity initially, because we will need to have Brownian bridges. Okay. And the third result is about the large deviations. First of all, why is the relationship between epsilon and eta? Why is that we cannot just prove that the limit as epsilon goes to 0 and eta goes to 0, we have the result? And the best way to show that is to think of the uncoupled problem. So this is not just the iconal equation you get by doing the logarithmic, the Hopf-Kohl transformation to the heat equation. Now this is a very simple problem. We can write down explicitly the solution. That's the solution to this problem. And if you want to claim that as epsilon and eta go to 0, that converges to x squared over 2t, which would be the analog of what we are doing, but if we were just dealing with the heat equation, you will need to know that epsilon logarithm eta goes to 0. And our condition is not that epsilon logarithm eta goes to 0, it's that epsilon logarithm eta to some, with logarithm in some power strictly bigger than 1 goes to 0. I don't claim that one cannot prove it, but it was already hard enough to prove it with any power bigger than 1, so then at some point you give up and you move on, and I will show you where this thing comes in, why the proof you need such an assumption. Okay, so now let me go to the large deviation principle. So the large deviation principle was, if you remember, it had to do with, I put hats because this is the Euler-Lagrange equations of the hat of the problem with the hats, with an initial terminal condition on the u epsilon to be 1 over epsilon. Same condition, that some kind of power type in terms of logarithm convergence. And then the result is that that constant that I had earlier, and I explained there, it's there in order to be able to have this to be 1 over epsilon, has a limit as epsilon and eta go to 0. And the u epsilon etas converge uniformly in that set to the solution of the corresponding limit problem, and this converges in L2. And the limit of the functionals, I didn't write it here. The hat is when we were taking supremum of minus L2 norm of R. These things have the same limit. So to do that, we don't rely on any tools from large deviation theory. And we have to study, as I said, the fundamental solutions. So I'm going to try to give you ideas of the proof going backwards. I'm going to try to do first the large deviation, then the well-posedness of the planning problem, and then at the end, if there are a few minutes, I can run through the rest of the talk, which is the estimates you need for the convergence of the Euler-Lagrange equations. All right. So let's look at the proof, in quotes, of the large deviation principle for the KPZ. So some terminology, because I will keep using that a lot. Let's call the limit problem, which is exactly that, as the physics problem. So this is the physics problem because that's what the physicists have solved, at least when everything is smooth, and I'll show you the solution to that. But I'm going to put a constant c here. So the result I stated earlier about the convergence, of course, will hold if instead of having 1 in front of the Dirac mass, we'll have some c. So we have a whole family of problems here, parameterized by c. Because the solutions are almost explicit, and you will see it in the next couple of transparencies, it's easy to see that if you make c go to infinity, so the only place for that problem the c comes in is a multiple, the c is a multiple of the, multiplies the Dirac mass at 1. So it's easy to check, because it's explicit, that as c goes to 0, the value of the solution at 0, 1 will go to 0, while if c goes to infinity, that goes to plus infinity. Okay, it's an explicit computation that one can do. The convergent results will be correct if we look at the problem with c delta instead of that. So that's one observation. The second observation, which is playing a little bit with the usual trick, multiplying, writing down the difference, multiplying one equation by the rho epsilon eta, the other by rho, it follows that the u c epsilon eta at 0, 1 and the u bar c at 0, 1 are both increasing in c. So these two quantities are increasing in c, and please go to 0 and plus infinity. And I'm going to use these two statements in order to prove that actually the c epsilon eta has a limit and conclude the large deviations. Okay, so first let's assume, so this is the constant, so let's first assume that somehow this goes to plus infinity, that they are unbounded, that epsilon 3/2 c epsilon over eta goes to infinity. Then that means that for epsilon, anytime I write a limit, it is with epsilon go to 0, eta go to 0, and epsilon minus logarithm eta to the kappa power going to 0. So that's the assumption of the limit. So let's say it goes to plus infinity, which means that for epsilon eta small, they would be larger than any constant we want. Comparing that problem with the c to the one that you start with 1, so this is the case where c is 1, and writing down the elementary, this Gauss-Lastry inequality, multiplying 1, as I said, it's the usual trick in infinite games, it's easy to see that you have this inequality. This is nothing else but the monotonicity assumption I stated earlier. So you have this inequality, the 1 comes because this is 1, and you have that, which implies that uc with this epsilon and eta will be less than 1. But we already know that the limit of this is that, and so that gives a contradiction to the increasing property of with respect to the c. All right? The limit of that has to be like that, but we know this has to be 1, that's a contradiction. So it cannot go to infinity. And similarly cannot go to 0. So along subsequences, the epsilon 3/2 c epsilon eta has a limit. Okay? So now, let's continue with that. I want to claim that there is a unique limit, that there are not two limits. So let's suppose that there are two limits, C1 and C2. Then I do the same argument. I do use the comparison. I use the fact that the limits are monotone at 0, 1, and the solutions. And that leads to a contradiction going through the usual identity. So if you have two limits, C1 and C2, then you compare the solutions to the physics problems with initial terminal conditions C1 delta and C2 delta. You write down the usual identity, and from here you find that at least on the support of the rho bars, this has to be the same, but that's a contradiction to the fact that the C1 and C2 were different. It's a simple argument that, of course, you need more than a minute to follow, but the only thing we're using is the strict monotonicity of the solution of the planning problem at the terminal condition, at the terminal time, with respect to the constant. And that tells you that there has to be a unique limit, So there is a limit there, and the rest follows from the previous proof. So this is an important fact that the probabilists couldn't get, that this thing has a limit. Okay. So now let me go to the planning problem. Okay, this looks a mess, but and forget the problem with the data. So forget what I'm writing there. And I'm writing down the explicit solutions the physicists have. Right? So the physicists are able to find an explicit smooth solution to that problem in a certain region. So the solution looks like that. In rho bar, so forget the etas. The rho bar is like a positive part of 1 minus x squared over LT, some domain. I don't have a check. Okay. So there's a domain like that, which I call O, and this is the domain that here. So this is time and space, 0, 1, 0, 0. So there's some explicit curve that looks like that, and inside there, the rho bar is like that. So the rho bars have compact support. There's 0 outside that set. And once you are there, you can figure out what the U is, because what they do is they are making that assumption that in that set, the U bar will look like it has an expansion, some function of time, which is there in order to guarantee that you have the Dirac mass, you have the conditions you want at 0 and 1, and some quadratic. And if you do that, if you make that ansatz and you plug it in, you find explicit ODEs for L and R and K. Okay? And all these papers I mentioned in physics, one or the other, are repeating this computation. They are not saying anything about what happens on the outside of that compact domain, but in that set, both U bar and rho bar are smooth. The only difference, by the way, with the eta is this thing, instead of being closed here, it comes out to there. All right? That's the only thing. Now, because the ODEs are explicit, you can figure out as t goes to 0, you have a very particular behavior for the rho, which is the strength of the curve there. This is going to go to Dirac mass. So the connection between rho and L is such that at t going to 0, t going to 1, this thing has to go to Dirac mass. So you have an explicit understanding for that. And the coefficients are important there. And here's a comment. If rho bar were 0, if we didn't have the rho bar there, that asymptotic behavior, the AT would be 1 over 2t. So this is a strange problem that the presence of the rho bar on the right-hand side for the Hamilton-Jacobi equation, which gives you, it's a forcing term, changes this classical AT, which is a 1 over 2t, to 2/3 over t. And this is important. I know it looks strange, and I think for a while we couldn't believe this calculation, but that's the difference. Putting a rho bar there makes that 2/3 over t, and which is important for the analysis, where if there was no rho bar at all, this would be like 1 over 2t. It's easy to see the 1 over 2t because you write down explicitly the solution to the equation. And this problem is symmetric, as long as it's smooth in time, 1, and therefore this, as it goes to 1, these things become like that. And there has to be a minus here. Okay, so the main difference is this is plus and this is minus, because as you go through the half, you have to reverse sign to go back to Dirac mass. And everything is smooth, so there is no problem here. So now how do you find a complete solution to the problem? Outside, we do characteristics. So on the outside, we are solving here, we are solving just the iconal equation, so we can use characteristics. The construction goes like that. Given any point here, you find the tangent from that point to that domain, and then you continue along the boundary of the domain. So that's the solution, outside the domain. All right? And notice that the way we construct it, we break, there is no symmetry here. If you are up there, the characteristics will not go there. If you are up there, you're going to come this way and follow that. And this is important because we want to maintain the fact that the U bar is a viscosity solution in the whole domain. All right? But once you have that, this construction, then you have a lot of information about what happens there. You just have to find that point, the tangent point, and then you know explicitly how you continue. All right? So that's the explicit solution to the what we call the physics solution, and the only difference with the eta is that the domain will come out like that, and this will depend on eta. By the way, I have to make this comment because I can tell you for years, because I have followed this course in your videos. He likes to use the red chalk. He thinks it's important to use the red chalk. So the red chalk, if you see it here, you see what it is. But in the video, this becomes almost not visible, especially if you're colorblind.
That's not the video problem, it's because you're colorblind.
I don't know. I mean, we have to see that. But for years, I have struggled to figure out what he writes once he uses the red. Well, if you use the yellow, I can see it. All right. So continue. So that's the physics problem. Okay, now I claim this problem is well posed. So let me at least show you for this problem why this solution I wrote down is unique. But to do that, I have to establish that I have the conditions I mentioned. So this, it's already a little bit strange because I told you that the behavior, it's different than 1 over 2t for the coefficient that goes to 0. But nevertheless, it turns out that the u bar xt is greater or equal x over 2t. Now, the way you do that is you write down the control formula, because after all, you have the viscosity solution, and you read it from there. What is strange is that this bad behavior, remember, there is the 2/3 behavior when you come down here from the inside. So if you go along such a curve and you come down, you get 2/3. But on the outside, you come down like 2t because you see the x squared over 2t there. So you're above it. You are always above it. So that's the easy part. There is a more technical thing which now controls, remember the solution a priori outside has to be like x squared over 2t or some constant. So we want to control the growth at infinity, and there's a result here that says that if you go far out, then the solution does look, the one you get, the u bar, does look like x squared over 2t, which is what you want. It's once you're concentrating at that point where you lose that behavior. Okay? And similar things for the u bar. Now, the u bar eta problem is smooth, so initially you will always go to x squared over 2 eta, 2 over t plus eta. Okay, so now we want to prove that this is well posed. I told you we have the conditions we mentioned. Now we need to prove the well posedness, so we need to know more about the behavior of as t goes to 0 and 1. So let's look at the t going to 0 solution. So I take any solution to the transport equation with the conditions 0 and 1 Dirac mass, and I compare it to the bar. So any solution like that will behave like this, with the x squared over 2t. Okay? It will look, since the Dirac mass, when you multiply it on u bar, we'll see the Dirac mass down here, and so this will go to 0. The integral, if you are far out, nothing happens. And that is related to the fact that, by the way, here I'm not claiming, when I write that down for the equation, I don't claim that the rho has a compact support. So that's not a trivial thing. You need to control a rho, which is just in the integral, not just in L1, against this particular solution, the U bar solution. And so you want to show that although a priori you don't assume that the rho has compact support, you have this behavior. And the final one is that as t goes to 0, I'm sorry, this is the last one. As t goes to 1, remember, look here, I'm not assuming that that rho at 1 is a Dirac mass. So it follows from the properties of the physics solution that as t goes to 1, this does behave like a Dirac mass. Okay, so that's something that has to be proved. Okay, there is no point to try to do that. Okay, now the uniqueness, once you have these estimates, the uniqueness is simple. You write down the usual identity. Again, that's the only connection with mean field games that I put in this identity, which compares two solutions. And now what we want to do is to show, as usual, that as theta go to 0, this disappears and that disappears, and then, so suppose we knew, let me go even back here, if we knew that this goes to something non-negative, non-positive, since this is positive, at the limit as theta goes to 0, this will go to 0. Okay? We don't claim that this, the only thing we can prove is that this is non-negative, as theta goes to 1 and 0. And then, once we have that, so suppose we have these two inequalities, which put them together says that the left-hand side is non-negative, then this integral will be 0, which is that limit. That implies that on the support of that, this immediately implies that the arbitrary solution rho is actually equal to rho bar, so it has compact support, and implies that in the support of rho bar, the two solutions have the same derivative in the support of rho bar. But since they solve the same equation everywhere in the U, and the solution outside there is found by following this tangent line and continuing there, once you have, okay, I'm still there, so they're solving the same equation in O, but since the same equation, then the derivatives, the time derivatives are the same. If you put these two together, you get that the difference between an arbitrary solution U and U bar on that set differ by constant. And then you use the construction of the solution, the fact that outside that set the solution is a viscosity solution, to conclude that that constant has to be 0, and you get the uniqueness. So you need this additional statement argument here because this identity only gives you information what happens to the support of rho bar. Okay, so all these things are correct as long as you can prove these inequalities at t equal 0 and 1. T equals 0 is simpler because there we are assuming that rho is a Dirac mass. So somehow things are simpler, but I'm not going to go through that. And the more complicated one is to prove that the behavior is good at t equals 1, where essentially we end up proving that both behave like a Dirac mass, both that the rho bar and the rho behave like a Dirac mass up there. And so that requires a little bit more detailed understanding of the singular behavior. Okay. Let me go now to the limit of the function. And I promised at the beginning I will tell you why we need to put this restriction on epsilon times logarithm minus logarithm of eta to the kappa power. So the first estimate you prove, you need some a priori bounds. And the a priori bounds you have is that the sup, as epsilon goes at this limit of the I epsilon eta is bounded. And then it's easy, because it's almost like a gamma convergence, to prove that I bar is less equal to the lim inf of the I epsilon eta. The hard part is to prove equality, and that's why we had to go through the Euler-Lagrange equations. But the condition, that condition here, comes in order to be able to show that this is finite. So what we need to do is build some particular element on the I epsilon eta is infimum, so we have to construct something that allows us to prove that. And that's where the restriction comes in. Once you have that, this is the only a priori bound. Once you have this, then the rest of it is just, we have epsilon and eta are fixed. All right, so I'm going to show you this construction. It's a mess, but it's the only proof I'm going to show you. So what we want to do is construct an admissible path, an admissible control of light for the I epsilon eta. So the I epsilon eta has the terms, you see them here. So the I epsilon eta, the rows have to solve that equation, and they have to keep everything finite. That's the energy. So the way we construct that is we work separately from a half to 1 and a half to 0, and a 0 to a half. We build two different solutions. We require that there is some continuity at the half so that it's a global solution, and then we try to prove that these solutions we have finite energies. Okay, so the upper part, again, is nice. And why is it nice? Because the eta comes at the t equals 0. So we need to do something uniform to take care of the eta, that is at t equals 0. And we need an estimate that is uniform in eta. So up there, you just get the solution to be, the candidate solution to be some rescaled version of the fundamental solution of the heat equation. So P is a fundamental solution of the heat equation. So you are assuming that this is a candidate rho. You plug it in, and you see that indeed it is solved with 0 if you put the right coefficient here, which is that. It's explicit computation. We want to show that this rho has finite energy. So a finite L2 norm, a finite energy at the half interval. So this is simple things. You put them there, and you see that if you take a particular choice of B, like that, why do we want that? Because we want B to become 0 at t equals 1, so that we can recover that the rho is a Dirac mass at 1. So that's a good candidate, nothing else. And if you choose the zeta in the right interval, this solution here, which is the easy part of the upper bound, has the properties we want. And finally, at the half, it takes that value. It's exactly the Gaussian with this value there, which is what the epsilon is at the half. Okay. And no constraints here on epsilon and eta, just epsilon. There's not, actually, in this calculation, there is no eta anywhere, because we are away from that. So the second part is where all the work comes in. So we're going to use the same idea, that the solution is some rescaled version of the fundamental solution. But the C now is going to be something more complicated. And it is going to be something that has to go to 0, because at 0, this rho has to be a Dirac mass. But we are asking that it goes to 0 in that slower than t, in that form, for some mu. Okay? Then the calculations, then this rho solves again the transport equation with that alpha. And we compute all the terms we have to compute. So initially, we want this to look like, it looks like 1 if we choose that's just the property of the Gaussian there. So nothing comes into that, that's automatic. At the half, again, it's an explicit formula that looks like that. And then if you combine it with the previous formula for the case of t bigger than a half, you figure out that indeed you can, as epsilon goes to 0, you can find the C0. It's an explicit constant that depends on mu. So these two things are continuous at the limit at the half. And now we have to check that this rho has a finite L2 norm and a finite energy. And that's where the constraint comes in on the choice of C. Is in order to obtain these two estimates. And, okay, so there's no point of going through the calculation here. The only point I'm making is if we choose, remember there's a kappa at the beginning. The assumption is that minus epsilon logarithm 8 at the kappa times epsilon goes to 0. If for that kappa you choose the mu a little bit larger, then indeed you can make the other part to have finite energy. And this is exactly where the condition comes in, is in order to prove this estimate. Once we have that, we can go. Now, can one improve the mu there to make it, get the kappa to be 0, in which case this will be true for a mu, most probably, but it's not worth spending energy on that. All right. And now we'll finish. I want to write down some estimates we get from that. All right, so what I showed you before is used to prove that the solutions we're using have finite energy. So because of the assumptions we made and the construction I put before, and since the rho epsilon eta and u epsilon eta are minimizers, we will have this a priori bounds. That's where we use the previous estimate, and from there on, it's hard to work. First one is we prove that some kind of local in space, estimating the H1 norm of the solutions away from away from 0. 0 is always a problem with the eta, so we have to work on that. So that's actually a very nice argument that tells you that if you can have an estimate, a local estimate in H1 of the u epsilon etas. And at this point, there's no way I can do that in 4 minutes. So I'm going to take you through there. So there's a group of estimates you want. It's always easier to get bounds if you stay away from 0 and 1. So that's such an estimate. Let me show you at least, because that's a nice proof, and it's a proof which has ideas about how one gets this estimate here. Then I think. Okay. So we want to get an upper bound on that quantity. This is the H1 norm of the solution. So we want an upper bound. Okay, I drop here the epsilon eta. So when I write u is u epsilon eta. Okay, so we want to get an upper bound on that. You do the obvious things. You multiply you want to integrate this. So basically, you just get an integral, you integrate that, and what you want to estimate from above is just this integral. So it's automatic that if you integrate in space from 0 to r, and at any h, you have this inequality. This is nothing else but taking that equation, integrating from 0 to r in space. And you get that. And the brackets here is the average, so it's like 1 over 2r of that. That's what the bracket is there. So that's automatic. Now we want to claim that somehow, and where do we get this? This we get it with the epsilon because it's the boundary condition when you integrate the second derivative. So this is the thing you want to control. You have the integral in time of the derivative at r, and you have the integral in space of the u, and you want to estimate the ux. Okay, so this reminds you a little bit of Poincaré inequality, since this is the average. So you can easily get that you have this upper bound on the average. So this is exactly how to average r u bar, u bracket. That's Poincaré inequality. And I'm skipping some steps. If you put everything together, you get this inequality here. So there's nothing here but copying the estimates from up there. This comes from there, and this is there already. But you notice there are two parameters here, r and k. I changed the theta to h there. There is an r and theta, and what you have on the right-hand side is nothing more than the derivatives of f with respect to r and eta times a factor, which is the L2 norm that is, you know an estimate of that. So this is like solving the inequality f of Rh, let's equal some constant, the r squared, that's why there is an r squared in the terminal thing, 1 plus the derivative with respect to r minus some factor times the derivative with respect to h. And this is now an analysis for this two-dimensional ODE. It's easy to show that you can choose things so that there is a constant that makes that bounded. The constant has factors here, but basically you prove that by contradiction. It's either bounded and you don't have anything, or it's unbounded, and then you prove that this cannot happen. Okay, so I think I'm done. So quickly, that's a new estimate, to estimate a Hölder norm of rho in time that is finite. So you need to prove something like that. That will give you an upper bound on the C0 alpha log norm of the U epsilon eta, which allows you to prove the local uniform convergence. And then what you need to do is understand the behavior near t equals 0 and t equals 1. And I'm not going to do this. I'm just going to conclude by saying that all these estimates we have is that along subsequences there are limits. And what we do is we compare the U epsilon eta with the U bar eta, because they have the same initial condition, the x squared over 2 eta. And then separately we prove the convergence of at the physics level, physics solution level, of the U bar eta to the U bar. And when you put these two estimates together, you get the conclusion you want. And I think I'm going to stop here. Thank you, and sorry that being such a mess at the end, but there is no way, it's a long paper, and there is no way that in an hour one can show you these things without destroying you. And so I stop here, and I'll do 3 different topics in the last 3 lectures. Thank you very much.
Thank you, Takis.